Hello everyone and welcome to this European Marine Board Third Thursday Science Webinar. My name is Ana Rodriguez and I am a Science Officer at the European Marine Board and I will be moderating the webinar today. Next slide please. So some housekeeping rules, if we can have the next slide, perfect. Please make sure your name is clearly entered when you ask questions so we know who you are. To ask questions, please use the Q&A box and it will be great if you let us know from which organization and country you are, and our speaker will then answer the selected questions. If you have any problems with Zoom, then please use the chat and we will help you. And just for your information, the webinar is being recorded and will be available on our website and on the EMB YouTube channel. Next slide. The focus of this science webinar is ocean deoxygenation. Specifically, it will talk about the impacts of deoxygenation in the Black Sea on ecosystem services, and it will use insights from the Bridge Black Sea expedition. This webinar links to our Future Science Brief number 10 on ocean oxygen, which discussed the role of the ocean in the oxygen we breathe and the threat of deoxygenation. And this document was launched recently in June of this year. And it also links to the Horizon 2020 Bridge Black Sea project, which is on advancing knowledge, delivering research, empowering citizens for sustainable and climate neutral Black Sea. Next slide, please. Our speaker today is Dr. Mustafa Yücel. He was a co-author of the EMB Ocean Oxygen document and is also Vice Director and Professor at the Middle Eastern Technical University in Turkey. And he is a co-coordinator of the Bridge Black Sea project. So I will leave the floor to Mustafa to give his presentation.
Thank you very much, Anna, for the invitation and for hosting me today. So I'll be trying to, let me first share my screen, of course. So I'll give you some recent updates from our Bridge Black Sea project. But before that, maybe from our viewers, there will be some viewers who are not that familiar with the oceans and what oceans are providing to us. Oceans, as you know, cover most of our planetary surface, and it's a big source of biogeodiversity. We still need to discover new habitats, and new species are waiting to be discovered in our oceans. Oceans regulate the climate, and new areas of products, bioproducts, such as new medicines, new cures actually for diseases may be hidden under our oceans. And of course, food security. Oceans are also big, they are of big importance for future food security of our planet. So all of these aspects we call ecosystem services or benefits of oceans to mankind. But maybe the most important service the oceans provide to us is the sentence you see here. We almost 6 of 7 breaths to seas and oceans. Maybe you heard half of the world's oxygen comes from the oceans, but as Anna introduced to you, our latest Future Science Brief, facilitated and published by European Marine Board, highlighted the fact that as much as 6 out of 7 breaths is linked to the oceans and linked to the photosynthesis in oceans. Of course, this is true when you really enlarge your geological scale, when you start your analysis since the beginning of the Earth, formation of the planet Earth. And in this publication, you will find many different useful bits of information and latest reviews, including how oxygen is linked to ecosystem services. You will also find the basics of oxygen cycle on our planet, particularly in our oceans. So for our purpose, actually, we will go, I'll take you to one of these so-called low oxygen or hypoxic areas we see in the world map. I'm not sure if you can see my mouse pointer, but we'll be discussing this little sea here called the Black Sea. But the problems Black Sea is facing, especially the special chemistry of the Black Sea with its almost oxygen-free deep basin, is also similar to many different places in the open oceans as well as coastal locations, which we call hypoxic zones or dead zones. So the oxygen issue of our oceans is global, truly global, but it's also an issue. Although you don't see oxygen yourself, it's a molecule dissolved in seawater or in air. Although you don't see it yourself, you will definitely see or feel the consequences of oxygen loss on our planet. And all of these aspects are very well explained on our brief. Also, we have tried to highlight in the publication, the first chapter, Professor Don Canfield had this very nice overview of the history of our planet and how oxygen evolution is linked to the planetary evolution. And it's important to note that our planet was not always oxygenated. Actually, only after the advent or evolution of oxygenic photosynthesis, the atmosphere was able to be enriched in oxygen. Of course, there are a whole lot of other processes, geochemical and physical processes, that contributed to the oxygen enrichment of our planet. But this is what you see on the left-hand side of my slide. On the right-hand side of my slide, you see on the upper panel the atmospheric oxygen levels as a function of today's levels. But in the bottom panel, I'm trying to show you the ocean chemistry underneath this evolving planet Earth. And at the moment, what we know, the recent evidence suggests that after about 2.5 billion years ago, so which means the last 2 billion years or 2.5 billion years of our planetary history, we have oceans oxygenated in its surface. So the top layer, the upper layer of oceans were probably oxygenated since that time, which is indicated in this blue color. And only in the past 400 to 500 million years after the Cambrian explosion, all of the ocean volume was oxygenated. Between 2.5 and 0.5 billion years ago, so during 2 billion years of Earth's history, the oceans were oxygenated in the surface and possibly sulfidic. We are still not sure. Sulfidic, hydrogen sulfide rich in some places, but mostly maybe suboxic or iron rich without much sulfide. So this is actually what pretty much the present day Black Sea looks like. The present day Black Sea in that regard, it's a laboratory for Earth's past, to understand Earth's past. It's a relic of, in a way, this ancient ocean, but it's also unique in many different aspects and challenges related to modern day problems that humanity is facing. That's why, aside from the fact that Black Sea has a very, very unique biogeochemistry and ecosystem characteristics, maybe contrary to this, it's also very productive, and its biodiversity, its biological production is very important for humans. In its upper layer, this upper oxygenated layer in the Black Sea supports different ecosystem services such as food provisioning in terms of fish, and different aquaculture activities are now booming in the Black Sea. But all of these blue economy efforts are now trying to implemented in the face of further oxygen decline, as we will discuss, further reduction in fish species due to overfishing and other factors, this growing human population in the catchment area, installation of new ports, new coastal structures. So all of these challenges are happening at the same time. And that's why actually the European Union, with the support of the countries around the Black Sea, since 2019, there's an important initiative going on in the Black Sea region. And let's say, the common thread in different projects, current projects and initiatives, is this document or agenda called the Strategic Research and Innovation Agenda. This was launched in 2019 and updated this year with the support of the Black Sea Connect Coordination Support Action, which is finishing this year. But the Syria, this document is essentially an updated guide on how to tackle multiple stressors such as oxygen loss or deoxygenation, and how to co-develop the research and innovation needed to support a sustainable blue economy. So today's topic, oxygen loss and ecosystem services, is a very important scientific topic that needs to be further studied because that's the primary challenge to address if you wish to continue to support a sustainable blue economy in the Black Sea. So you cannot think of blue economy without the science, without the specific environmental characteristics of the Black Sea. And now there is a new implementation plan of this Syria, which was just published a few months ago, and I will come back to this at the very end of my speech. Now a little bit to focus on the Bridge Black Sea project. In 2020, again, as a part of the Horizon 2020 program, 2 projects were funded called Bridge Black Sea and Doors Black Sea. So these projects are working together, and altogether they actually represent a 20 million euro package that addresses the Syria. Partially, of course, it's impossible to address the whole Syria with this funding, but there is more to come. Of course, these projects are now starting to implement the Syria and paving the way for future projects. So Bridge Black Sea, yes, is one of those projects responsible with implementing the Syria. And currently there are 31 partners from 14 countries. And the coordinator is my institution, METÜ IMS in Turkey. The core concept of this project is to advance Black Sea's marine research and innovation to co-develop blue growth pathways under multiple stressors for the sustainable utilization of ecosystem services. So the project has 3 nodes, and all of these nodes are towards this bigger aim. But this notion of considering the very peculiar characteristics of Black Sea ecosystem is ingrained in every aspect, every task, every work package, and every node of the project. So again, for those of you wondering the definition of stressor, because you may be hearing about it in different contexts, at least in natural systems, what we mean by stressors is that they are phenomena caused by natural processes or by direct influence of human activities, and they can damage ecosystem health, harm organisms, or hurt the well-being of coastal populations. And often they don't happen in isolation. Their effect, it can be synergistic, can be combined to impact the Black Sea. And then that's why we use the term multiple stressors. And the project is addressing tools or developing new tools to address the multiple impacts of these stressors. Here you see 9 stressors in the outer rim of this graph: pollution, eutrophication, warming, invasive species, deoxygenation, sectoral activities, overfishing, and acidification. These are the type of stressors which, as a result of all the stakeholder engagement activities in the Syria development process, these 9 main stressors came forward for the Black Sea. You may also call them pressures in different settings. And the Bridge project also is building its work over these 9 stressors. So of course you can still add more and more stressors, but we found that the 9 main stressors, they are the most important ones. The project approach includes, of course, basin-wide Black Sea work, but also we have this focused areas where we concentrate more, and we call these areas pilot sites. And each of the Bridge Black Sea pilot sites we have predefined based on existing stakeholder engagement and existing project results. We have predefined a certain ecosystem services. Here you see, for example, habitat maintenance was suggested as a key service in Northwestern Black Sea. Food provisioning was important or has been important for the Varna-Burgaz pilot site. The Bosphorus site near Istanbul was defined as an important fish migration route. That's why it's important food provisioning service providing area. And the Batumi area on the other side, the Georgian coast, was found to be important site of tourism. So that's why we defined this area, or we thought the cultural services would be a good focus in this area. So, and we have thought of our stressors as how they are acting on these services. So, of course, it's a very complicated analysis, and we are still developing our work in that regard. But the first step towards this, we have already taken. We have already generated some results, and here you see 9 breach Black Sea stressors, abbreviated as, for example, W as warming, DO2 as deoxygenation, OF as overfishing. We have gathered through a very intensive collation activity and searching available databases, etc. We have generated a sort of index of data readiness for these different pilot sites with regard to each of the 9 stressors we are working in the Breach Black Sea project. Long story short, green means good. We are ready. We have enough information or data to at least assess and start some policy development towards that stressor. But the red ones are the ones that we really need more information, or we need to uncover more hidden data. But if you look at the deoxygenation, which is today's topic, you'll see that the 1 is very good, of course. I should also add that 0 is bad, 1 is good. Most of the pilot areas we are working on, they are relatively low in data readiness with regard to addressing deoxygenation. You may think that oxygen is a relatively standard parameter for which data exists or data is collected, but most of the times, even the deployment of an oxygen probe or taking a bottle sample for oxygen is not that straightforward. You need specialized personnel or calibrated equipment for that. So that's why the readiness is not that high. But of course, comparing it to acidification, abbreviated as A here, of course, the readiness is much higher, because for acidification, we need a lot more information. Many more parameters need to be measured, such as pH, alkalinity, etc. So that's why we have came up with these that sort of data readiness analysis to see where we are. But of course, this doesn't mean that we are not able to assess the latest situation with what we have in the Black Sea. And the data readiness exercise also guided our expedition work, which you see some photos from some of our expeditions. On the left, that's Mare Nigrum, Romanian vessel. On the right, you see Bilim, Turkish research vessel. Other research vessels of the partners were also active, such as Academic of the Bulgaria, Marmara of TÜBİTAK, and Alemdar of Turkey, Istanbul University, Georgian Batumi colleagues also, they mobilized their research vessels. So the project actually has been, again, back to my pilot sites map, has been quite active, especially in southern and western. Unfortunately, due to war on Ukraine, we were not able to do any field work in northern Black Sea. I should also state that. That was not the original plan. The original plan was to really all field work would happen almost simultaneously, so in a synergistic manner. So we gather data from all sectors of the Black Sea, but we had to, of course, adapt to the challenging conditions. Even going out to sea was not so easy. In 2021, after the outbreak of the war, we had to postpone most of our field work due to the mines, sea mines, risk of the sea mines. Only towards the end of 2022, we were able to go out to sea and be very careful. We managed to do our field work. Most of the times, the research vessels, for example, on the Romanian side, since they are closer to Ukraine, they had to work only during the day and they had to anchor by night. In Bilim, we were a little bit more comfortable in the middle and eastern part of the Black Sea. But anyway, we were able to really go out to sea. We were very happy to be able to do that. And many young people, also students, young marine professionals also joined us in our project. We have a big capacity building aspect. Here, for example, you can see some photos from the Romanian cruise, Mare Nigrum cruise. But just to show you a few of our most recent findings, as I promised in the beginning, Here on the right-hand side, you see a typical screenshot when you're out to sea and collecting data. I'm sure some of you are already doing that, but for those of you who've never been to a research vessel, this is the type of plots and data streams you're looking at all day in a typical oceanographic expedition. Of course, you are also sampling from bottles or from sediments, as you see in the photos. But here I would like to direct your attention to this green line here. That's oxygen, that's dissolved oxygen. On the left-hand side, we are looking at depth. So depth 0 on top and going deeper. So this particular graph shows you the upper 200 meters. I think this is a little bit offshore in the Romanian waters. And the top, as you can see, the top 60 to 80 meters is pretty much oxygenated. If you're not familiar with units, 8 to 10 milligrams per liter oxygen is good. That's pretty much the maximum amount of oxygen you can dissolve. When you shake a bottle of water very hard, that will be basically the level of oxygen you are able to, that's your physical limits. But after 60 to 80 meters, you see that the oxygen levels rapidly decline. And after about 130, 40 meters, it's pretty much gone. So that's Black Sea. And deepest part in the Black Sea is about 2,200 meters. So it's a very deep basin. And you can imagine that actually a majority of the volume of the Black Sea is pretty much anoxic. Anoxic meaning no oxygen at all. Hypoxic meaning there is still some oxygen, not enough maybe to sustain a healthy biological population, but there is still some oxygen in the definition of hypoxia. Here, these points are the latest in terms of what we have occupied as coordinates, station coordinates in the Black Sea as a project. I think one of these weeks also, again, Mare Nigrum will be out to sea and will be occupying also some stations in the Bulgarian side as well. So this western area will be also filled in. So, but as you can see, we are very much covering we are able to cover western and southern Black Sea in this project, but we have a quite extensive data sets from these locations. Yes. But these locations are indicative of what the ships occupy when they go out to sea in open water cruises. As I said, in the pilot areas also there's extensive sampling, day trips or diver trips, diving activities. So we collect a lot more data at the pilot site level at a very high resolution, just to highlight that. So many different data sets also flow into our databases from those pilot sites as well. Again, just to show you some of the recent results, this is we are looking at, again, water depth profiles from the Black Sea, from the Turkish expedition in December 2022. Here I'm showing you profiles of data from two locations, this M44, M43, and N10Q15. So what we are looking at here is, again, the y-axis is indicative of the depth. Here it's plotted in terms of decibars, but you can roughly equate this to depth for the purpose of our presentation. And here we are looking at density, potential density, but imagine that you're looking at the density of the Black Sea. And the reason I'm showing is that to illustrate that the Black Sea is a very density stratified sea, unlike most of the oceans. There is a very, very shallow mixed layer, but after about 50 to 60 meters depth, density starts to increase rapidly to levels. And the reason is that the upper part of the Black Sea is dominated by this river input, more freshwater input, whereas the lower part, deeper part, the majority of the Black Sea is waters originating from the Mediterranean. But they are, of course, they have a much, much higher residence time. So they don't get mixed up with the upper part of the sea that often. So it's kind of isolated from the air. That's one of the reasons why oxygen is gone in the deep Black Sea. Another reason is, of course, the high production that I have already mentioned, which is good for fisheries, for food production, but in a way, it's also the other reason for the oxygen loss in the Black Sea. On the right-hand side, now what I'm doing is, since Black Sea is so stratified with regard to density, we typically plot our results with regard to density. So in the right-hand side, for example, we are looking at temperature in degrees Celsius, and now I'm using the data that I used here in the x-axis. I'm using those data here in the y-axis. So instead of depth, I'm looking at density layers in the Black Sea. This is typically how we plot our oceanographic data in the Black Sea. We plot our parameters against density to see, because if there is any change occurring, if we want to understand that change, we cannot just look at its depth distribution. We need to see if that change is happening at the same density layer or not. For example, here we are looking at temperature, and in the Black Sea temperature profiles, we have this typical minima in almost all locations. The exact location is different in each station, but between a certain depth, we have this feature, which is historically called cold intermediate layer. Currently, we find that in December cruise, as well as in other recent cruises, we have found that this layer is not colder than 8 degrees Celsius anymore. But from historical data, from 20th century data, we know that this layer was much colder than 8 degrees Celsius, as low as maybe 6.5 degrees Celsius or 7 degrees Celsius. Now it's at least 1.5 degree warmer. So when you look at analysis such as this is analysis published by European Environmental Agency. Okay, surface waters are warming up, and Black Sea is one of the fastest warming areas in that regard, along with the Mediterranean and the Arctic. But this warming is not only happening in the surface, it's also happening in the deeper layers of the sea. And with this happening, of course, in the specific case of the Black Sea, the thickness of the cold intermediate layer is also decreasing. And we know that this is an important layer bringing oxygen to the deep Black Sea or ventilating the sea a little bit. So we see a major physical shift, for example, in the case of the Black Sea, analyzing these temperature data. And this is directly relevant to oxygen loss in the Black Sea. On the left-hand side, you see a result from the group of Marie-Laure, also part of our Breach Black Sea project. So they have used the World Ocean Atlas data as well as Argo float data to illustrate the oxygen loss in the Black Sea. Both the inventory is decreasing in terms of mole per meter square, but also the depth at which, I think here they have selected 20 micromolar level, at which 20 micromolar oxygen is also showing, coming to the surface. On the right-hand side, it's a work under preparation, work of Barish and Volodymyr from our institution. This is again the entirety of the Black Sea. These are CTD data and bottle oxygen measurement data from 1960s, I think as old as 1960s. And again, there's still a lot of analysis to be done. It's preliminary, but at least until 2000s, there's a declining trend. But after 2000s, actually, the decreasing trend is not so clear. At least it's not as prominent as the Argo data or other types of data. Which brings me to the recent expeditions. Again, coming back to our recent December expedition. This is again the southern Black Sea, most of the southern half of the Black Sea occupied by Bilim, by our vessel. In blue, you see data from historical data that we have compiled in the same area, same half of the Black Sea, from southern Black Sea. And the red is actually our data from Breach Black Sea project. On left-hand side, sensor measurement, oxygen sensor, right-hand side, validation measurements by Winkler oxygen titration, which both agree very well, and they both show that as a twist of plot, the recent, at least the shape of the profile is similar to relatively oxygenated periods of the Black Sea, which means that the shoaling of the oxycline, which was shown in other data sets, at least as of December 22, we've found that at least the disappearance depth of the oxygen is not that shallow. So it's still similar to the 20th century, let's say, distribution. And it's a little bit a surprising result. We were expecting to find a much worse condition with regard to oxygen disappearance, but this came as at least good surprise for us. We are also looking at what happens once oxygen is gone. So microbial communities use different electron acceptors to do respiration, such as nitrate. That's why you have this nitrate loss and ammonia accumulation with depth. Phosphate also is accumulated over depth, etc. So Black Sea becomes a huge nutrient stock as well as you go with that, as anoxia becomes more severe. The reason we are doing this, we are also trying to understand how the inventories of nutrient change over time in the Black Sea, how, for example, hydrogen sulfide changes in the Black Sea. It's an important toxic gas, which is detrimental for, of course, the upper ocean habitats. And typically when oxygen is gone in the Black Sea, sulfide starts to appear, not immediately, but after a few tens of meters, after a layer called suboxic zone, hydrogen sulfide starts to increase. So another question we are having in mind, and we are still mining our data to answer this question, if the hydrogen sulfide layer in the Black Sea is also approaching the surface or not. So it's a parameter for which we have much less frequent measurements. But in the past 2 years, we have intensified our measurements, and we are trying to compare our results to some other data-intensive periods in the history. One of those periods is, I would say, 90s and early 2000s. There were, again, many cruises. There was a big collaborations between regional countries, European countries, and United States, and many quality data were generated in those years. And at least with regard to hydrogen sulfide, and this is also fresh new plots, by the way, we are finding that the hydrogen sulfide onset densities are also pretty much similar to those previous findings. So I just tried to actually highlight a few of the results from our field expeditions. Our analysis, of course, continue, but at least we are able to say that warming in the surface and deeper layers continue. So there is no halt in that. Black Sea absorbs heat and it gets warmed up. But a plot twist would be the rise in the oxycline seems to be stabilized in the past 20 years or so. And there's no sign of rise in dense layer of sulfide onset. That's pretty much certain. But I'm basically writing the sentence with a big caution. The oxygen inventory, we will still calculate the oxygen inventory, and we will then know the exact trend in oxygen loss, because the onset or disappearance depth of oxygen may be similar to historical layers, but the inventory may be still decreasing. So, and we are still working on those calculations. But as you can see, a direct impact of warming and deoxygenation is not that easy. Physical events, changes in current regime, cold intermediate layer currents, and biogeochemical dynamics. I mean, there's a lot of redox reactions in the Black Sea, microbes involved in this. They all act in synergy to create the picture that we see in the few times we are able to go out to sea. But we can, at least in the decadal time scale, we can assert that the biogeochemical regime in the Black Sea exhibits a certain degree of resilience. And we can best understand this in the suboxic zone oxygen and sulfide gradients, and further work on modeling and resilience analysis in the frame of Bridge Black Sea will uncover the limits of resilience of the Black Sea in the near future. So all these works, now that the fieldwork component of our project is pretty much at a mature level, let's say, now we are able to feed into other work packages in the project. As you can see, we have 9 work packages with the 10th work package on management. But we are now at a stage where work on ecosystem resilience, modeling, adaptive management scenarios, all these works will be fed by the new data as well as historical data that we are collating. And then we will really start addressing how the oxygenation is linked to other types of dynamics and how the oxygenation will impact the services that I have described to you in different corners of the Black Sea, which are then relevant for supporting blue growth in the region. Yes, and all these work packages and activities still they continue, and we will hopefully update you in future stakeholder events happening intensively in the region. So before closing, as I promised, I would like to actually again go back to the Syria, the Black Sea Strategic Research Innovation Agenda, and the implementation plan that we launched this year. Especially the implementation plan is now in a mature shape. It's published, and it consists of 12 teams under 25 strategic joint actions. So these are type of priorities or well analyzed and stakeholder validated, let's say, strategic joint actions, which are ready to be funded. They are ready to be supported, and they are ready to be implemented. So we invite all of you to take a look at this. There in the you can find the plan in the Black Sea Connect website. And but just to highlight a few of the topics that are present in this document. As I said, there are 12 teams, and each team contains 2 or 3 joint actions. For example, we have allocated an entire team to digital twin of the Black Sea, and there are 2 strategic joint actions under this twin. So one of them is, of course, developing the twin itself, building on what has been going on, of course, and the other strategic joint action is advancing AI-powered decision support tools for ecosystem-based management in the Black Sea. So there are these sort of statements in the plan, but they are, I think, very important for especially funding agencies or other types of public bodies or private sector who are looking for supporting science and blue economy in the Black Sea. Another important priority is One Health approach for Black Sea and safety of Black Sea coasts, which is also very relevant in the context of the ongoing war. And of course, capacity building, blue skills, they are still there, waiting to be supported in the Black Sea. So with this, I again highlight I encourage you to take a look at this implementation plan, which was launched in Brussels, European Parliament, with the support of all of you, support of Marine Board, our parliamentarians, many different stakeholders. Thank you for being with us in this Black Sea journey, and I'm ready to answer any questions related to the science itself or the policy process itself as well. So thank you for your attention. Anna, you are muted.
Sorry, thank you. Thank you. I was saying thank you very much, Mustafa. Just to remind everyone that if you have any questions, please put them in the Q&A box. So yeah, Mustafa will answer them. I will select them and Mustafa will answer them. I will just start with some questions. So one thing that was quite interesting is that the 90% of the Black Sea is anoxic, you were saying?
Yeah, it's pretty much, yeah.
Yeah, well, first of all, is this used to kind of infer between past oxygen, how the ocean was in the past, and how that like parallels how that influences the functioning and how
that's a great question, Anna. The 90% estimation is it's coming from present day observations, of course, but the Black Sea has been pretty much a calibrant, let's say, especially the sediments of the Black Sea and the composition of sediments of the Black Sea has been traditionally considered as a proxy or is thought of representing the ancient ocean, the deposition happening in the ancient ocean. So in a way, the sedimentary composition of, for example, pyrites or isotopic composition of sulfur has been always linked to the present-day Black Sea's chemistry. And then when a rock composition was found to bear a similar value in terms of sulfur isotopes, then it was linked to a chemistry similar to Black Sea's chemistry. That's in the beginning, this picture of the ancient ocean chemistry is actually pretty much coming from what we learned from Black Sea and similar, of course, modern-day anoxic systems.
Okay, very interesting.
Yeah.
And does this high anoxia in the Black Sea affect its functioning? Is it less productive than other seas, or how does it relate to other seas?
Of course, overall, when you think about the whole ocean volume, of course, Black Sea contains less multicellular life. So in that regard, of course, you can consider it as a less productive ocean. But if you just compare the upper, let's say 100 meters of the world ocean, upper 100 meters of Black Sea, then Black Sea is actually more and more productive, a lot more productive. So it depends on which layers you compare. But of course, overall, 90% of the sea is without any oxygen, which means that there is no multicellular life. In that regard, yes, it's less productive, but when you look at its surface, it's more productive.
Okay, so the deep anoxia, it's not influencing the surface. There's kind of a separation between the productiveness in the surface and in the deep.
Actually, this is something we are looking at. It's also an open question. How this deep processes, deep redox processes, or deep respiration processes, how that controls the upper productive layer is an open question. I don't have a direct answer for that, but still indirectly, there's a huge body of chemically reducing elements and gases, and they all act as a sort of oxygen sink. So I would still say that this big body of chemicals, hydrogen sulfide, methane, other things, they still act as an oxygen sink. So it avoids, even if you bring oxygen to Black Sea through currents or through other mechanisms, this big body of chemicals will act as an oxygen sink. So in that regard, I think it controls how thick the oxygenated upper layer will be also in the future.
Okay, thank you.
Yeah.
We have a question in the chat from Britt, another science officer at the European Marine Board, and she asked, how can your research be applied to help improve and implement environmental and blue growth policies in the Black Sea?
This is, well, the first step in implementing any policy, as you know, is you need to be informed about the environment you are interested in, you want to develop policies about. So since Black Sea has been a big policy focus of Europe in the countries as well, but European interest intensified in the recent decade. The need for new types of information, the need for environmental trends, but most importantly, forecasts. I mean, how the environment will look like if we do this, if we do that. So under different scenarios, how the environment will change. That is quite relevant for policy. And we have designed our project actually to generate these sort of policy supporting outputs as well. But first and foremost, I think for policy purposes, you need to understand how the environment evolved in the past history, in recent history, of course. And how it will continue to evolve under business as usual scenarios, but also under multiple blue growth pathways if they are implemented. So as a project, we are trying to, in a very general term, we are trying to produce these sort of scientific outputs for policymakers. So I think that's the first link to policy. We are filling a gap in knowledge, but not also, we are not only just generating new knowledge, but producing new predictions, new what-if scenarios for the Black Sea. That's the type of things policymakers really need, I think.
Okay, thank you. And is there already any policy insights that you have already gained from the Bridge project? Any main
very good
ones?
question. I think the biggest policy insight I gained so far is the Black Sea is really very, very special in terms of its environmental characteristics. I have already talked about this. It's very unlike another corner of the ocean, or it's very much different from Mediterranean Sea or Atlantic Ocean. So these are the European sea basins, as you know. Maybe it's more similar to the Baltic Sea in terms of challenges. So a very special program needs to be implemented for the Black Sea. You cannot just implement another solution developed for another basin. So I think the first thing I learned is, and this is very well agreed, by the way, by the policy side, that the special characteristics of the Black Sea need to be always considered. So this I think learned. But another insight, I recently tried to actually develop this insight, but of course, with the project, we will understand better how, especially in the past 2 decades, the environment changed. But we may, it may be possible that the environment is not as bad as it used to be in the 80s or 90s, which may have a slight, maybe a reason for this, maybe this increased cooperation which happened after 90s during 2010s, which unfortunately stopped now or slowed down now, but there may be a clue of how intensified regional cooperation in this policy-directed research, it may have helped the Black Sea a little bit, or at least in slowing down the degradation. Still very early to conclude, but I think in the Bridge project, we will, together with all of you, we will, in 2 years of time, we will have better assessments for this, but we may have, my insight is that cooperation works, actually. Long story short, it may have worked in the past and it may still work, it will work in the future. So we need to go back to, again, cooperating more intensively. But as you see, the degradation, like in Baltic Sea case, the stakeholders, countries were able to stop the degradation of the Baltic Sea. I think in the Black Sea is equally possible. That's my biggest insight so far.
That's great news. And what were the main management actions that helped improve it? Is it known?
Well, in the Black Sea, I don't know the exact year it was established, but for example, there is a Black Sea Commission, which is, of course, has its own challenges, but it has been very instrumental in having the countries working together towards stopping of the pollution, which damaged the ecosystem a lot in the later part of the 20th century. I think another important policy action was maybe indirectly related to Black Sea, but what happened in the continental Europe, with the expansion of European Union into the Eastern Black Sea, with the inclusion of Bulgaria, Romania, with implementing cleaner technologies, polluting less the rivers draining from that side into the Black Sea, that may have helped the Black Sea as well. So policy actions related to land also, they are very relevant for marine policy. So I think that needs to be analyzed as well from our side. But I think those policies also helped Black Sea, and they will help also if implemented in other parts of the Black Sea too.
Great, yes, and policy actions on land can also help deoxygenation. So that's also
definitely
relevant.
As our brief, our brief was very clear on this. Actually, the oxygen cycle is relatively simple. On one hand, you have production by algae, or you can physically, bring oxygen to your water. But then there is consumption of oxygen. All life consumes oxygen, including us. So this simple balance, actually, when you actually remove some of the load, some of the organic load that the sea is bearing, then you will have less oxygen consumption. You will have a higher chance of re-oxygenating our seas. So yeah.
Yes. Okay, there's a question in the chat from Cem Hazarbechi. Sorry if I mispronounced that, Cem. He asks, what is the intended scope of a digital twin? I suppose it's linked now to specifically the Black Sea. I don't know if you have any insights on what.
Yes, this is going to be about Black Sea. Of course, the twins are now produced or developed for different scales. Sometimes at the scale of a bay or harbor, or some people talk about the global ocean twin. But no matter your scale, you will have first of all you will need some demonstrators, I think, in different corners of Europe or of the world. So we think Black Sea is a good candidate for such a demonstrator because we are already. Well, first of all, you need a very good physical and biogeochemical model of the sea. And in Black Sea, we have this. We have many models now in Bridge project running in parallel for comparison. So we have this backbone, we have the structure already settled. And twins are not just mathematical models, they are more than that. They include this what-if scenarios, they include to some extent some near real-time information from the environment. I think Black Sea is, in terms of scale, it's possible to gather different information and build this twin on top of existing very, very strong models that we already have. So in that regard, the scope is the Black Sea itself, but the scientific scope of the twin would be this mathematical model supported by other aspects of it, twin scenarios, data feeds. So that's where we are at the moment. So this is something we suggest as a future call. Actually, this is not something we have started yet, but the models are there. Yeah.
Okay. Yeah. So this is also very relevant to one of the main aims of Bridge, which was to inform policy.
Yeah.
But you say it's not yet part of Bridge, right? So you don't use these models to predict scenarios.
No, at the end of Bridge and Doors project as well, both projects will leave validated working models for the Black Sea. They will leave a very rich set of data sets, both historical as well as what project generated. And now we are suggesting that a twin should follow up these projects to really build. But the scenarios, of course, or the digital aspects or the development aspects of how the end user or how the policymaker will interface with the twin, that's not part of either Bridge and Doors. That needs to be developed, and we also need to learn about this, of course, from other bases or from other twins under development.
Okay. We have another question in the chat about what do you think are the main threats for the conservation and protection of the Black Sea, specifically from a climate change perspective? And I know you mentioned the main stressors of pollution, warming, deoxygenation, and overfishing. Yeah. So I don't know if in the future, maybe one of them will be more important for the conservation, or how that will affect.
In terms of external pressures, I think overfishing is still a big threat to the Black Sea. Warming is, of course, it's happening very fast in the Black Sea. So warming deoxygenation is a consequence in a way, but in terms of external pressures, I think warming and overfishing. Well, maybe beyond overfishing, this loss of biodiversity also. I think they are the main threats in the Black Sea. Pollution is something, as I said before, in past decades with regional cooperation, it's something that is partially addressed. We know at least the way forward to tackle that issue. So I, at least assuming that threat will already be tackled with, because countries are already well informed, there's policies around that, they just need to implement the policies to cut the remaining pollution. But for warming, I don't know what can be done. And for biodiversity loss, we need to do more, definitely. Maybe a new mechanism or tool could be protected areas, which doesn't exist in the Black Sea, at least in most of the Black Sea coast. So protected areas. But to do that, you need a lot of information. Maybe you need these sort of digital twins to really help policymakers design these sort of solutions. Yeah. But those are the main things that I expect that they will become more and more important next 10 years or so. Okay.
Yeah, it's already good to hear that pollution is improving. And indeed, warming is a bit more difficult to tackle because it's more on a long-term scale that we need to make actions to improve that. But is there anything for overfishing? Is there already any talk about cooperation or how to improve it, or is it difficult or complicated to reduce the overfishing?
I think it's complicated. Well, there are certain regional efforts in place towards this, such as GFCM. The Black Sea, GFCM is the name, it says Mediterranean in its name, but Black Sea is also in the scope of GFCM. That's General Fisheries Commission of the Mediterranean. Countries are working a lot on this aspect, but I think there are issues with regard to monitoring and management of existing fleets, gathering data from who's doing what. But overall, you see the result. We have now less number of species in terms of economically viable species. Biomasses are going down, so somebody's doing something. But I think, maybe protected areas just no-take zones, these sort of things need to be in place rather than just putting some fines to fishery fleets. Yeah. It's another topic, of course, which I'm not an expert of, but when I look at the results or the trends, you can see that that's one of the main problems in the Black Sea.
Okay, so just to remind everyone to put any last questions you have in the chat, as we will finish the webinar soon. And just in the meantime, one last thing that I wanted to ask you, it was interesting to see that the oxygen has actually maybe increased in the last, I don't know, since when you said 2010 or 2000, the last 20 years maybe. Is it known why this could be? That's good news, but is there any explanation for it, or?
We don't have an explanation for it yet. It came as a surprise to us, but well, the data only tells us that the profiles we collect lately, and they look similar to a little bit better times, 20th century. They are still bad, of course. I mean, you still don't have oxygen, 90% of the Black Sea, but at least the disappearance depth of oxygen didn't become more shallow. Why? One reason could be related to physics. So if you have a little bit more mixing, I mean, what we have observed could be a very intermittent thing. Maybe there are cycles of 2 years, 3 years that we don't realize. We look at long-term trends, but environments don't change linearly, as you know. So it may be the case that there is a different physical regime in the past few years, which kind of pumps more oxygen into the deeper dense layers. So it may be one explanation, but to do that, we need to look at, well, the project is looking at physics in the past years, but we don't have an answer for it. Another thing I have in mind is what controls oxygen, as I said previously, is also the concentrations of reducing species. So it's not only biology consuming oxygen in the sea, chemical reactions can also consume oxygen. So if you have a lot of sulfide, methane in the sea, or iron, manganese, they can also consume oxygen. So it may be the case that the concentrations of these intermediate redox species might have decreased a little bit. Maybe that's related to climate change, river inputs, some particulate inputs might have changed in the past decade. We don't know yet. So redox reactions is one candidate. Different physics is another candidate that comes to my mind. But we have a general assembly of the project next week. That's one of the things I will present and hopefully gather more input from our partners on this issue. Yeah.
Very interesting. So just at the forefront of knowledge and science. But the projection is for the long term that the oxygen will keep declining in the Black Sea?
Of course, I mean, the projection with the processes that we know that operates in the Black Sea, oxygen decline should continue because you are warming up the sea. As our oxygen brief also stated, warmer seas holds less oxygen. So that's a very, very simple law. And with warmer seas also what happens, as we have also explained in the policy brief, the seas becomes more stratified as they get warmer, which means that it will be harder to mix the upper layer and lower layer, but which apparently didn't happen in the Black Sea yet, despite warming. So that's why I have used this term twist. So there are some things that we know which controls oxygen cycle, but apparently there are also some other things that we don't know and fully understand yet. So.
Okay, thank you very much. And maybe just the last question, I don't see any more question in the chat. What is the key knowledge gap that you think should be addressed? Is there any key knowledge gap that is important for the Black Sea management or for oxygen dynamics in the Black Sea?
Yeah, there's a lot actually still. We have a lot of data gaps as you saw. I mean, we are not able to cover different corners of the Black Sea. An important gap in our knowledge is Black Sea is very sensitive to external inputs, to river input, to atmospheric inputs. We don't have a good handle on these inputs. I mean, again, in the project, we are trying to update or upgrade those estimations, but a lot of data are lacking in terms of what's going on in the atmosphere, what's going on in rivers. Yes, there's a lot of monitoring in rivers, but the data generated most of the times is different. They are generated for different purposes. So they are not the type of data that you can use for your models, for example, for marine systems. So I think the biggest gaps is this exchange of Black Sea with its boundaries, atmosphere, rivers, land. We need more different projects maybe addressing those gaps, or different smart approaches, because the approach that I described here is about the sea itself, about the marine system itself, how we study its surface, its depths. But I think this connection between land and sea and atmosphere and sea is still very important, and we are lacking good observations and models on in that interface. Yeah. So that's a big gap for the Black Sea.
Thank you very much, and that links actually perfectly to our next webinar, which, if I can ask Fernanda to share the slides, I'm going to introduce just shortly before we finish what our next webinar will be about. So our next webinar will be in October, the 19th of October, and we will use it to launch online our document, Building Coastal Resilience in Europe. This document will have been launched just one week before at the Eurasian conference, and it talks exactly about what Mustafa was saying that is missing, that we need a better connection between land and sea to build this coastal resilience. So it will be a very interesting webinar, and we invite you all to attend it. It will be presented by Sebastian Villasante, and there will also be an opportunity for Q&A with the rest of the working group and invited panelists. So please register, and we look forward to see you there. And with that, I would just like to thank you again, Mustafa, for your presentation and for the Q&A.
Thank you.
And all of you for your participation. Thank you very much.